Hey everybody, in this video I want to talk to you about the most important theorem in all of statistics, the central limit theorem. Central limit theorem, among other things, is why we think normal distributions are so important in statistics and why we basically have a whole chapter, in fact 2 chapters dedicated just to them in the book. So let's go to the notes. So here is where we are in the notes. We just finished the whale and human example in z-scores. And now I want to talk about the central limit theorem. So I'm going to go through the central limit theorem several times. I'm going to start by just describing what it does. So here's the actual theorem. Your book does something that I think is completely insane and does not have the central limit theorem just in a box right at the beginning of the chapter saying, here it is. Here is the most important thing. I wanted to rectify that, so I did it. I put the central limit theorem in a box right here. Don't worry about the wording. It's going to sound super confusing at first. So let me explain what the central limit theorem says. The central limit theorem says that if we take a bunch of different samples from the same population, and their samples are all the same size, we find the mean of each one of those samples and make a distribution out of those means, then that distribution will be normal. And not only that, but we can talk about what the mean and standard deviation of that distribution are as well. So that's the idea of the central limit theorem. It's not so it's using a concept that is called sampling distributions, which is to say, if we take a bunch of different samples, find a statistic about each of those samples, and then graph them, make a histogram, I should say, out of them, then what shape do we get? And if the statistic that we find about all those samples is the sample mean, then the shape that we get is a normal distribution. We end up using this a lot. In literally every section. Yeah, I think this comes up in literally every section from here till the end of the course. So yeah, you can tell we use this a lot. Now the central limit theorem actually says a few more things other than what I just said, but that's the basic gist of it. Is if you take, not when I say a bunch of different samples, that's not really true. Central limit theorem refers to if we take all the possible samples, which for instance, if we're talking about like women's height, like we were up here, right, height of American women, then there are going to be trillions upon trillions of possible samples. If we took, let's say, samples of 100 American women or whatever, there are going to be an enormous number of them, way more than there are things in the population, right? The sampling distribution actually has a lot more things than the population does now. So when I say a lot of samples, what I really mean is all the samples, right? All the millions or billions or an ungodly number of samples that you could possibly get, right? Where if I change even one person out for a new person, that's an entirely new sample. So here's what the central limit theorem actually says. It says that if you meet one of two requirements, you only need one of these two. Either the size of the samples that you're taking is relatively large, with just the cutoff, just sort of the generally accepted cutoff is 30. Don't get too hung up on that as a magic number, but that is the generally accepted number. I'll return to that. That's one of the requirements. If your samples are large enough, or if you happen to know that the population you are drawing those samples from is normally distributed, then you can say that the sampling distribution of the sample mean is normal. And it's got the same mean as the population, and a standard deviation that has shrunk by a factor of root n, where n is the sample size. So the sampling distribution and the population are two totally different things. Sampling distribution is the distribution of all possible means, or a distribution of all possible whatever statistics. For now, we're just going to do it with means. It's a distribution of all the possible means that you could get if you took every possible sample. The population is all of the individual data values. Those things are completely different. And I know that that's not necessarily obvious from me saying it, so let me draw a picture here. I guess I got my old stuff on the whiteboard. Oh no, I don't. Good. So I have two things, right? So here is my population distribution, some normal distribution. Here is my sampling distribution. I'm deliberately drawing that differently, taller and skinnier on purpose, because the central limit theorem tells us that the standard deviation of the sampling distribution shrinks, which shrinks from the original population distribution, which here, so I have the empirical rule on. You can see what that means here. If I make my standard deviation smaller, look what happens, right? Taller and skinnier. That's what I was trying to draw, right? If I make my standard deviation larger, distribution gets spread out. Make it smaller, it gets taller and skinnier. So I was trying to get that across in my picture here, right? So here's my sampling distribution. Here is my population distribution. Now, the reason I brought this up is I want to make this point here. So let's say that these guys are data values, right? This is filled with millions and millions of dots here, right? So let's say this is a distribution of American women's heights, right? Like we were using before on the worksheet. So every one of these dots is some woman, right? Some American woman is her height is every one of these dots. In the sampling distribution, that's not what these dots are, right? These dots are not people. They're not individual people. These dots are the means of different samples. So for instance, this dot right here, right? So this dot right here might represent these various women here. Like all of these women are going to go in a sample, right? These, whatever, 2, 4, 6 women, right? If this was my sample, then all of these together, right? The mean of these would be this dot here. So that's the way that populations are different from sampling distributions. They're just distributions of entirely different things. Up here, these are women's heights. Down here, this is sample means, right? So this is not one person. This is one sample of 6 people, and it's the average of their heights. Each of these dots are one person. These dots are means of a sample. So entirely different stuff. The central limit theorem tells us nothing about this. Central limit theorem only talks about this, the sampling distribution, not the population. Okay. Central limit theorem has, like I said, one of two requirements. Either your samples are relatively large, with 30 being the relatively large cutoff, or we happen to know that the population is normally distributed, right? From prior experience, right? We've taken a lot of samples of this before. We just know what the population or what the distribution of the population looks like for whatever reason. If we know one of those two things, then we can say that the sampling distribution of the sample mean is normally distributed and has a mean that is equal to the original population mean and a standard deviation that is equal to the original population standard deviation divided by the square root of the sample size. So sigma over root n. Now, this long explanation and long complicated explanation is, in a practical sense, it's very easy to do all the math you need. Basically, all you have to do is divide the standard deviation by the square root of the sample size, and that's your sampling distribution of x bar. That's it, right? So literally, a couple buttons on your calculator, you found the sampling distribution. You do have to check that you meet one of these two requirements, though. It doesn't have to be both, just one of them, but you do need to meet one of them. Yeah. So the thing that I think is most interesting here is not the mu and sigma over root n. So the mu is kind of interesting. We'll talk about that in a second. Sigma over root n, this is the thing that people end up doing, right? That's the calculation you have to make. And so that's the thing that gets stuck in their brain as the important part or the interesting part. That's not at all the interesting part, in my opinion. In my opinion, the interesting part is this n. Because one thing you might notice here, we are not assuming that the population is normally distributed, right? That is one of the potential ways that we might know this is normal. But this is normal even if the population isn't, which is weird to think about. Right? How do I get these exponential wait times, right? Exponentially distributed wait times, and I take a bunch of, I take samples and find means of each sample, all of a sudden it's normal? Yes. Yes, not the population that's normal, it's the sampling distribution, but yes, it is normal, or the sampling distribution will be normal in that case. That's why the central limit theorem is so interesting, in my opinion. The fact that the standard deviation shrinks actually makes perfect sense if you think about it, and we'll talk about it in a little bit. Okay, yeah, that's really what I wanted to say there. Yeah, that thing I just said is what these paragraphs say here. You're welcome to pause and read, or just read in the notes. Okay, so sampling distributions. I was talking about sampling distributions before. That the idea of a sampling distribution is you take all the possible samples from a particular population, find some statistic about them, and then make a distribution out of those statistics. That's a sampling distribution. The one we're doing, and in fact, pretty much, I guess there's another one we'll do, but the one we're really focusing on here is means. What if I take the mean of each sample and graph it? We could find the standard deviation of each sample and graph those, and you would get something that is not normally distributed, actually. You get something that has a F distribution? No, chi-square distribution, which we'll learn about much later. You could, instead of doing the mean, you could find the median of every sample and you graph that. And I don't remember what the shape of that is, actually. I think that one might be normal as well. You could find the third quartile of every distribution and graph that, and that would be another sampling distribution. You could find the maximum of every sample and graph that. So you can do this for any statistic, but the central limit theorem is specifically saying, if we do that for sample means, what do we get? And that turns out to be a thing that we want to do a lot of. So that's what a sampling distribution is. It's a statistic that you find about all the possible samples and then make a distribution out of, right? I'm thinking of it in terms of pictures and graphing, but it's really just any distribution, any probability distribution, any way you want to visualize that probability distribution. It doesn't have to be a graph, but that's my way of thinking of it. All right, so that's what this is talking about. All right, I want to do an example for you, show you how this works. It's a big example, right? Here it is. I'll do number 7 too. We rarely get to this one in class when I do these, but luckily there's no upper time limit, and you can just skip this if you want to, or read through it, or watch me do it rather. Okay, so I want to make this point before we start here. Unless you're reading very carefully, it can be very hard to tell whether you should use the central limit theorem or not. So here's how you tell. If you are taking a sample with a size bigger than 1, you're going to need the central limit theorem. And I'll talk about why when we do it. That's basically the cutoff. That starts here. And the reason you can tell it starts in part E in this example. The way you can tell that is, I'm going to very briefly read through this. I guess we'll read the setup and then we'll very briefly read through A and D, and I'll just point out the difference now. You can tell. So the wait times for Dr. James Elmore's patients are uniformly distributed between 0 and 30 minutes. So it's not normally distributed. They're uniformly distributed. X is going to be the random variable that measures the wait time of a randomly selected patient. That is to say, X is approximately U 030. Notice this is not an N, this is a U, right? That's uniform distribution with a left edge of 0 and a right edge of 30. So that's the rectangle. A through D asks about one patient at a time. C, find the probability that a randomly selected patient. D, find the probability that a randomly selected patient. E, let X bar be the average wait time of a randomly selected group of 30 patients. Once you start talking about groups, that's when you need the central limit theorem. When you're talking about individuals, you don't. Okay, so let's do this problem. Okay, I'm going to call up a whiteboard so we can draw things. There's this stuff, let's clear all that off. So what I'm going to do is start by drawing the population distribution. It's uniform from 0 to 30 minutes. So we know that looks like this. This is 0, 30. And if you recall, this is going to be 1 over 30. Now, we're going to need to know the mean and standard deviation of this distribution, because this is the population distribution. Because when we start using the central limit theorem, notice that the central limit theorem tells us what, oh, come on, scroll a little faster. My computer's being a little bit of a pain here. The central limit theorem tells us what the sampling distribution of X bar is in terms of the original mean and standard deviation in sample size, right? So we need to know mu and sigma, and we don't actually have that yet. Now I'll let you flip back through your notes or find what the formulas for mean and standard deviation of uniform distribution are, but I'll also just write them up here, where the mean is A plus B over 2. Whoa, it started moving around on me. Over 2. Pardon me, sorry, it started moving the window on me. And the standard deviation was B minus A over the square root of 12, minus A over root 12. So we should find what those things are before we start going. This one's easy. A plus B over 2 is going to be 15. So right in the middle. This one is going to require a calculator, so I'm going to go get one. B minus A over root 12 is going to be 30 minus 0 over root 12, or just 30 over root 12. 30 divided by the square root, where's that is, of 12. So that is 8.66. So I'm going to go put that as my standard deviation. Where was I at? Here. 8.66. About equal to 8.66. Okay. So there are my mean and standard deviation, right? My mu and sigma for this. Now notice this is not N15, 8.66, because this is not N. This is not normal. This is uniform, right? So it's U030. And so all the calculations that I'm going to do are going to be based on this. Or so when I'm looking for probabilities for one individual person, well, this is the graph of all the individual wait times. So that means I'm going to use this picture to determine my probabilities. So let's go look at those. Oh my gosh, come on, computer. Sorry, I'm trying to convert a video here and it's going slow. Find the mean and standard deviation of X. So notice that I'm using capital X here for the name of my distribution, and little x is going to be one person's wait time. I'm using capital X bar for the name of my sampling distribution, where little x bar is going to be one sample mean. So we did A and B already. Find the probability that a randomly selected patient has to wait at least 20 minutes to see Dr. Elmore. That is, find the probability that x is greater than 20, or greater than or equal to, I suppose. But again, continuous distribution is the same thing. 20 minutes, so that's here. 20. So we are looking for this probability there. Or we're looking for that area there. The area is probability, so this area is the probability I'm looking for. Well, you can tell the base here is 10, the height is 1 over 30, so 10 times 1 over 30 is 1/3. So probability that x is greater than 20, or I guess greater than or equal to, equals 1 over 3. All right, let's see what the next question, part D, was. Find the probability that a randomly selected patient sees Dr. Elmore in less than 13 minutes. Okay, so other direction this time. So that one is over here, so mean of 15, so there's like 13. So part D is asking about that area. Well, that's 13 over 30, right? I hope that's clear enough. Probability that x is less than 13 is 13 over 30. So I'll say this is 0.33 repeating. This is, let's go find that. Let's go turn that into a decimal just so we have a nice even basis for comparison. We certainly don't have to, but we're going to be finding decimals later. So having a decimal now to compare to decimals later is going to be kind of nice. So 0.4333. I guess I can actually equal 0.433. There we go. Okay, easy enough. Population done, right? This is the probability that one person has to wait at least 20 minutes. This is the probability that one person gets in less than 13 minutes. So now the questions from here on are going to ask about groups of 30 people. And so because we're asking about groups, we're going to need the central limit theorem. So let's go see what those questions look like. Let x bar be the average wait time of a randomly selected group of 30 of Dr. Elmore's patients. So this is n here, n equals 30. Find the mean and standard deviation of x bar, capital X bar. Name of the sampling distribution is a capital letter, of course. And so I'm asking about distribution of capital X bar, so we're going to use the central limit theorem. So the central limit theorem says that, well, let's go over here. The central limit theorem says that, what am I trying to say here? The distribution of capital X bar is approximately normal with a mean of mu and a standard deviation of sigma over root n. So for us, n is 30, sigma is 8.66, and mu is 15. So that is n with a mean of 15. So that doesn't change. Standard deviation is the standard deviation of my population divided by the square root of the sample size. So 8.66 over the square root of 30. Let's go find out what that is. 8.66 divided by the square root of 30. 1.58. 1.581. It's good to be extra precise with standard deviation, by the way. A very small change in standard deviation can change your calculations quite a bit. So I'm going to go maybe one more decimal place than I usually would. So this is a normal distribution with a mean of 15 and a standard deviation of 1.581. So let's go ahead and sketch that. I think I might Get rid of this. Yeah, I'm going to get rid of the top step. In fact, I'm gonna erase all this and start at the top. I don't think we're going to need this anymore. So 15, 1.58. All right, so let's clear all this. So we know that X bar, that is a capital X bar, is approximately normally distributed with a mean of 15 and a standard deviation of 1.581 minutes. And so I'm going to sketch that. Yep, 15 here. One thing I do want to point out is my students often want to find some place to put this on the graph, and we'll do something like this, right? 1.581. Do not do that. 1.581 does not go on this graph. The things on this x-axis here are x bars. They're averages of samples, right? The average value in a sample. This is not that. This is not the average value in a sample. It does not go there. So don't be looking to put the standard deviation on the graph. It does not actually go on the graph. It is okay if you want to mark this off in standard deviations, right? If this is 15 and you want to put the next one is 16.581, and then the one after that is, what would that be, 18.162, right? You can do that, but I never bother. That seems like an excessive amount of work to me, so I don't bother doing that. So for me, the only place I ever write the standard deviation is in the label, right? When I'm labeling my graph. Normally I would write N15 1.581 here, but it's literally like 1 inch above it. So I'm not going to relabel the graph. Okay, so from here, the questions are going to be the same. What's the probability that a group of 30 takes more than 20 minutes, or a group of 30 has an average that's less than 13? So let's go see exactly how I asked those. Sketch a graph, we did that. Find the sampling distribution, we did that. Okay, find the probability that a randomly selected group of 30 of Dr. Elmore's patients has an average wait time of more than 20 minutes. Find the probability that little x bar is greater than 20, not x bar, because asking about a particular, the average of a group, right, which is not an x. X is one person. The average of a group is an x bar. Okay, so the reason we want the sampling distribution for that, by the way, this is all the x bars, right? This is the graph of all the possible x bars. So what we're trying to find is, what's the probability that one particular x bar is over here, right? So since this is a graph of all the x bars, and I want to know what's the probability that one particular x bar is greater than 20, this is the graph I need to look on. So probability that x bar is greater than 20 is, well, we can't calculate that without a calculator, right? That's what we need normal CDF for. This is just a normal distribution. I know it's a sampling distribution, but it's normal. So I want to do normal CDF from 20 up to infinity with a mean of 15 and a standard deviation of 1.581. So that's what I'm going to do. Let's go to the calculator. Normal CDF. The lower bound was 20. The upper bound was infinity, so just a lot. Mean was 15. Standard deviation was 1.581. There we go. 7.82 times 10 to the negative 4. So very, very, very unlikely. About 8 times in 10,000 it would happen. So not very often at all. All right, so this number's tiny. So again, scientific notation, move this decimal place 4 to the left. You move it 1 to get past the 7, and then there's 3 more zeros. So it's 0.000782. Right, so very unlikely. Let's flip back to the notes. Find the probability that a randomly selected group of 30 of Dr. Elmore's patients has an average wait time of less than 13 minutes. Right, in probability notation. Sure. So again, we're talking about a group of 30, and we're talking about the average wait time of a group of 30. So what did we say? I forgot what it was, 782. Yeah. Oops, this is 0.000782. The next question asked about the probability that the average was less than 13. We're gonna do it the same way, of course. So same mean and standard deviation, mean of 15, standard deviation of 1.581, and we're gonna go 0 to 13. So normal CDF, 0 to 13. This is an example of where you could go negative infinity up to 13 if you wanted to, but that it wouldn't change the answer at all. Or it won't change to 10 decimal places, the answers will be the same. So whichever one. I'm doing 0 because I'm thinking of it in a practical sense, right? You can't wait less than 0 minutes. 0.1029, so 10.29%. One thing I want to point out, both of these numbers are significantly smaller than the corresponding ones from previous parts. So in parts C and D, I think, we asked about what's the probability that X is greater than 20, and we got some relatively, or we got like 33%, right? For the probability that X was less than 13, that was 43%. These are way, way smaller, and the reason they're so much smaller is that the standard deviation changed a lot, right? It went from 8.66 to 1.581. And just to give you an idea of what that looks like on a graph, it looks like this. So right, so here is what a standard, this is a normal curve, believe it or not, with a standard deviation of 8.66. It's very hard to see because it's so flat. Which way is it? Yeah. Right, you can barely even tell that it's curving down. It is, but it's just curving down very little. As opposed to 1.581. Right, so notice how less fat that is, right? That's much taller. That's what the difference between 8.66 and 1.581 looks like. And by the way, I'm aware that the 8.66 was for the normal, or was for a uniform distribution, not a normal one. But what I'm trying to do is give you some picture in your mind about how much more bunched up 1.581 is than 8.66. Here, let me change the windows. Can I do that here? I should be able to. Yeah. So let's say this went from -4. I'm going to do like -50. Let's do like, no, let's do like -30 to 30. Yeah. The y can go to like -0.1. Yeah, let's try this. -0.1 up to 0.4. Okay. This will maybe give it a little bit of better of a picture. Right. So this is, so here was the population. Right. There's something that looks like that. That's the normal distribution equivalent of the population. And here is sampling distribution, right? Those are very, very differently shaped things, right? One is like that's the relative difference in what standard deviation changing that much looks like, right? It really squishes the distribution in. The reason I bring that up is that if I'm, so here, this observation, we had, what was it? It was, what? Oh my gosh, I've totally forgotten. Hang on one second. Oh, right. Sorry, I'm not centering this in the right place, am I? 15. There we go. And then the observation was 20. Whoa. Whoa. Oh, I see. Well, it's k equals 20. So the likelihood of getting 20 or more minutes for an average is very small, right? It's the area under here. Tiny, very, very tiny, right? You might say there's nothing even under there. There is. If we zoom in far enough, we will see that there is a little bit of area to the right of that. Here, let me do this. I'll shade it in even. I know you can't even see it yet, but that number that we found is still going. Hang on. Still zooming in. It's there, I promise. Oh my goodness. I've never tried to zoom this far before. Why is it not working? It won't zoom anymore. Oh my God. It's so small. There's area in here, I promise. You're just gonna have to trust me on that. Desmos won't zoom in far enough? Really? Holy moly. All right. So that's why it's so unlikely, right? The calculator is finding the area to the right of this that is between this graph and 0, which you can't even see on the computer. Yeah, I'm gonna have to spend some time scrolling out, it looks like. Oh, yeah. All right. So I'm gonna reset it this way. X-axis 20 to 20. Oh yeah. No. So x-axis is gonna go. What did I say? Minus 30 to 30, and the y-axis can go from negative 0.1 to 0.4. There. So you can see there's area to the right here, but it's really, really tiny. Oh, that means not 3, that means 15. What the heck? There we go. I was gonna say, that seemed awfully small to me. All right, well, I'm too far into this video to redo it. You're just gonna have to live with me being ridiculous here. There's the area that we found. This thing right here. Thought that seemed awfully small. This shaded area right here is what we found. Okay. Sorry for the confusion there. Sorry for my own confusion. I just had my mean set wrong. So that area is what the calculator found. All right, let's go back to the calculator before I embarrass myself any further. That was this one, right? That was this 7.82 times 10 to the negative 4 was that tiny blue area I just found. If I wanted to find the area to the left of 13, right, the 10% that we just found, shade left, that is, I can just set this to 13. That's this. So 10% of the area under here is blue. The point I was originally attempting to make here was the following. The standard deviation for the sampling distribution is smaller than the standard deviation of the population. So when you are asking about things that are away from the middle, you get smaller areas because there's more area clustered up around the middle. And so when I'm asking about less than something that's away from the middle, that number goes down. If I'm asking about something that is greater than something that is to the right of the middle, that number goes down because all the area on the edges gets squished into the middle. Right? So that's why those numbers are so much smaller. Right? So the original population had this probability that x is greater than 20 was 0.33, and probability that x was less than 13 was 0.433. Right? It was those guys. Because this 20 is farther away from the middle than the 13 is, right? 20 is farther away from 15 than 13 is. This 33% shrank down to this tiny number, right? 0.078%. This 13 is a little bit closer to the middle, so it shrank, not quite as much, because you got some of the area that's close to the middle. But that's why these numbers are smaller, is because they're on the edges, and the edges get smaller when you shrink the standard deviation of a normal distribution anyway. So let's erase this stuff and go find some more probabilities. Question H. Oh, that was H, sorry. Question I. Find the probability that x bar is between 10 and 15. No problem. Normal CDF, left edge is 10, right edge is 15, but it's the sampling distribution because we're asking about x bar. So that means that I'm going to use mean of 15, standard deviation of 1.581, as opposed to 0.866 for standard deviation for the population. So normal CDF, bottom of 10, top of 15, mean standard deviation as given, 0.499. So almost exactly half, which is kind of interesting. This actually makes perfect sense that it's almost exactly half if we go look at the picture. Right, so 10 to 15, so 10 is over here somewhere, 10. Let's do it this way, 10 to 15. So that was asking about what's the probability that x bar is in here. Well, it's very big. In fact, it's almost exactly half because there's very little area over here. And we know that because normal distributions are symmetric. And 15 and 20 are the same distance apart as 15 and 10. So there's the same area over here as there is over here. So I actually know what that area is. It's this. 0.000782 is over here. Well, the area to the left of 15 is 50%. The area between 10 and 15 is 50% minus this, which is very small. Right, it's actually this number right here. All right, let's see what else we got. All right, so we've got this number, or we want to find this probability that x bar is greater than 30. We're going to get a tiny number. It's like 10 to the negative 20 something. Let's just do that real quick. It's going to be normal CDF from 30 up to infinity with mean of 15, standard deviation of 1.581. It might actually just give us a 0. I don't think so, though. Excuse me. Normal CDF, 30 up to infinity. Yeah, not quite. It's times 10 to the negative 21. So 1.2 times 10 to the negative 21. Now, I would argue that this number should be actually 0. Right? So in a normal distributions definitely go forever. So certainly the area in the normal distribution would be this. However, if you think about what these things are measuring, what numbers we're measuring here, these are all supposedly wait times or average wait times for groups of 30. Well, the average wait time for a group of 30 people can't be more than 30 minutes because the maximum wait time for any person is 30 minutes. So we're getting a tiny number, 1.2 times 10 to the negative 21. And when I say tiny, like that is indescribably tiny. But my argument is it should be actually 0, since you can't have an average over 30, since nobody's individual wait time is over 30 minutes. So average wait time can't be over 30 minutes. So the reason I put this question in here is to remind you to constantly be thinking about what that number that you got means and what it's measuring. And it's very easy to get caught up in just writing down numbers and not thinking about, all right, what's the consequence of this number? What does that number mean? And you want to constantly be reminding yourself of that. Okay, find the median and the 25th and 99th percentiles of X bar. And I want to explain what those numbers mean, of course. So the median is actually quite easy to find because normal distributions are symmetric. I'm gonna erase all this just so I have a little bit more room here. Normal distributions are symmetric. So the median and the mean are the same thing, as is true of any symmetric distribution, has the same mean and median. Distributions that are non-symmetric don't have that property. Because the median is where half of the data is to the left and half is to the right. The mean is sort of, you want to, I always think of it as where the distribution would balance if you made it out of wood, for instance, right? So in this case, the mean and median are the same because it's the same on the left and right. In this case, they're not, right? The mean is here-ish, something like that. If this distribution goes on forever, the median is infinity. Or the median is infinitely far out. You know what, just to avoid all the problems with infinity, let's just say this stops right here. In that case, the mean and the median are not the same because this is skewed to the right. Right, most of the data is over here, and then the tail with all the outliers is to the right. And so it pulls the mean to the right, but doesn't change the median. Right, so the mean and median are not the same here, but they are there because this is not symmetric and that one is. Let's just okay. So the median is 15, same as the mean. I also asked for some sort of percentiles that I don't remember, 25th and 99th maybe? Hey, I did remember, 25th and 99th percentiles. So we're just going to use inverse norm for that. That is not the right share, pardon me. 25th percentile, something like this. 99th percentile over here, right? So 25th percentile is saying, all right, well, what if we have 25% of the data to the left? Like, what is this number? And the 99th percentiles, same thing, but 99% to the left, right? So there'd be 99% over here and 1% to the right. And so we find those the same way. We use inverse norm, right? Same way we did before. So I do inverse norm, area of 0.25, mean 15, standard deviation 1.581. I'm leaving it on left as always. 13.93 is the 25th percentile of wait times. 90, that was not the right button. Pardon me, let's try that again. Inverse norm, same thing, 0.99. 18.67 is the 99th percentile of average wait times of groups of 30 people. Okay. So, I also asked to explain what these numbers mean. This number, 13.93, this means that of all possible groups of 30 people, or I should say samples, of all possible samples of size 30 of patients of Dr. Elmore's, we would expect about 25% of the sample means of those groups to be less than 13.9 minutes. Similarly, if we look at all possible groups of size 30 and we find the average wait times of those groups, we would expect about 1% of them to be bigger than 18.68 minutes, and 99% to be smaller than 18.68 minutes. That's what percentiles mean in this case. All right, let's look at the last couple questions here. All right, I got old cranky Bob here. And by the way, this problem that I'm going to do right here is not similar to the homework problems at all. So feel free to fast forward through this bit and just get to number 8. But I want to set this up. This is sort of set up for future problems. That's really where we're going with this. Future chapters, I mean, like this is going to be more like chapter 9. But I just want to introduce it now. So here's the idea. Old Cranky Bob is one of Dr. Elmore's grumpier patients, as his name suggests. He has some doubts about whether the wait times in Dr. Elmore's office are as short as Dr. Elmore claims. He thinks Dr. Elmore is making him wait longer than he says. So Bob, Old Cranky Bob, randomly takes a sample of 30 of Dr. Elmore's patients and finds an average wait time of 18.4 minutes among those patients. Now, here's what Old Cranky Bob is going to do with this information. He's going to look at this and say, all right, Dr. Elmore says that the wait times are uniformly distributed between 0 and 30 minutes, so the average should be 15, but my average from my sample, me being Bob, was 18.4 minutes. How unusual is that? Right? If the wait time is actually 15 minutes, what is the probability, or excuse me, if the average wait time is actually 15 minutes, what is the probability that this group of 30 wait times has an average of 18.4 minutes? Right? If the real average is 15, what's the probability that we would get an average of 18.4 or more? So in other words, if this is what the graph actually looks like for all the wait times, how likely is it that our sample ends up over here? If it's very unlikely, right? If the probability that we get here is really small, that would make us think maybe the average isn't actually 15 minutes, right? Either we got a crazy sample or else the average is actually higher than 15 minutes. So let's see what the probability is there. Well, I'm just going to do normal CDF of 18.4 to infinity with a mean of 15 and a standard deviation of 1.581. CDF of 18.4 up to a lot with a mean of 15 and a standard, oh, I messed that up. Mean of 15, standard deviation of 1.581. There's actually about a 1.6% chance to get that, right? So not very likely, not wildly unheard of though, right? 1.6% doesn't come up a lot, but it comes up sometimes, specifically 1.6% of the time, right? This is not like 1 chance in a million or something. This is 1 chance or 2 chances in 300 basically. So we want to figure out, should Bob complain? Bob is cranky but reasonable. He's only going to complain if he gets an average wait time so large that it is less than 5% likely that he would get such an average or larger. In other words, he is determining his complaining strategy based on this area right here. And if this area is 0.05 or less, he's going to complain. Well, the area we got was 0.015, which is smaller. So old cranky Bob is feeling cranky, and he's going to let Dr. Elmore know all about it, because this area was 1.5%, which is smaller than 5%. And you might say to yourself, Jeff, that is a ridiculous way to determine whether you should complain or not. That is how statisticians do it. That is, in fact, the way people do things. I know that sounds silly, but this is you're going to do this a whole bunch of times. It's called the hypothesis test. Yeah, we'll return to that in chapter 9, but just heads up, that's what we're going to be doing, is we're going to find an area and say, is this so unusual that it makes me think something weird has happened? And if so, then we're gonna make a decision based on that. You'll see later. But this whole process right here is going to be one you'll get really familiar with. Okay, let's look at one last thing. So the central limit theorem is written in terms of means, but with a little bit of cleverness, you can figure out how to apply it to totals as well. Your book does this in perhaps the most confusing way possible. Yeah, you could probably make it more confusing if you tried. By just introducing it as something totally different that has different formulas and different everything, and it doesn't. It's literally the same thing. You do have to do a little bit of converting. But yeah, so they have a whole section on this. 7.4, I think 7.4. I'm not at all interested in doing it that way. I'll show you how I want to think of it. And then you are more than welcome to read the book. And if you prefer to think of it the book's way, go right ahead. I suspect you won't. I do not like the way they did it. Anyway, here's the idea. So again, central limit theorem written in terms of means. But if you are clever, you can turn things into sums by converting all the means into sums. And here, I'll show you what I mean. So it is the annual sumo convention at the Tokyo Ritz-Carlton, and it's always an adventure to see if the elevators will hold up. The passenger elevators have a weight limit of 3,000 pounds, and the weights of the sumo wrestlers at the convention are normally distributed, with a mean of 390 pounds and a standard deviation of 50 pounds. Let X be the total weight of 8 sumo wrestlers, not the average weight, the total weight. So what would the average weight of 8 sumo wrestlers need to be for their total weight to be 3,000 pounds? That's pretty straightforward. The way you find averages is you take the total and divide by how many there are. So if I take this total of 3,000 pounds and divide by 8 sumo, divide it evenly among 8 sumo wrestlers, that'll tell me what the average weight would have to be. So let's do that. Calculator. If I take 3,000 pounds, the weight limit of the elevator, and divide it by the number of sumo wrestlers, this is what the average would have to be among those sumo wrestlers. So the question here is, what's the probability that if we get 8 random sumo wrestlers, so a sample of size 8, that the average is at least 375, right? That'll tell you what the probability is that the elevator breaks, or that they exceed the elevator's weight limit. It probably wouldn't break the elevator on the first try, but dangerous. Right, so the average, if the average is over 375, then the total will be over 3,000. All right, let's see what the second question says. Find the probability that 8 randomly selected sumo wrestlers riding the same elevator will be enough to exceed the elevator's weight limit. Okay, so what we're going to do is we're going to answer the question not what is the probability that the total weight of 8 sumo wrestlers is over 3,000 pounds. We are instead going to answer the question, what is the probability that the average weight of 8 sumo wrestlers is over 375 pounds? Because that is the way the central limit theorem is worded. So that's the way we're going to do it. We're going to do it in terms of averages rather than in terms of totals. So let's go grab a whiteboard and do that. Oh my God, come on. All right, so I'm going to erase all this stuff. So we can say that X approximately normally distributed. Well, that tilde didn't go very well. Normally distributed with a weight of our mean of 390 and a standard deviation of 50. And we know we have N equals 8 sumo wrestlers, right? That's how many are trying to get on the elevator. So then X bar for 8 would be approximately normally distributed with a mean of the same mean, 390, and a standard deviation of 50 over the square root of 8. which is n 390, and then we go get a calculator. $50 divided by the square root of 8, which is 17.6, let's say 17.68. Uh, 17.68. Right, and so our question was, what's the probability that the average weight of those sumo wrestlers is going to be greater than 375? Well, we answer that using not x, but x bar, because it's a sample of size 8 instead of just one sumo wrestler. And so this is going to be normal CDF. Well, here, let's draw this. So this is n 390, 17.68. There's 390. And 375 is over here somewhere. It's less than 390. And I want to know what the probability is that x bar is greater than that. So it's going to be some big number, right? I'm expecting 70, 80%, something like that. So 390, 17.68. And by the way, this is, oh, oops, that's not where I want to put that. This is the sort of situation in which you could use the empirical rule if you wanted to get a quick estimate. So let me do that before I calculate. I actually don't know what the answer is here. So this is like, so 375 to 390, that's 15. So that's like 1 standard deviation, about. And so we're about 1 standard deviation below the mean. Well, there were no, it's 68% is within 1 standard deviation of the mean. So 68% would be in here, but then there's all this to consider as well. The easier way to calculate this is that if there's 68% within 1 standard deviation of the mean, that means that there's 32% outside of 1 standard deviation. So there's 32% down here and up here, so I have to divide it by 2, so like 16%. So my initial guess is 84% here. It's actually a little bit more than 1 standard deviation, so I'm going to say 90% is my guess. All right, so I'm a little bit further to the left than, oh no, so I'm not quite as far to the left as 1 standard deviation. So I'm going to make my guess 80%. Let's see how close that is. So we're going to do normal CDF. Normal CDF of, we're going, the bottom end was 375. The upper end was a lot. Mean is 390, and the standard deviation was 17.87. Is that what it was? I literally forgot. I'm sorry. I have to flip back. 17.68. %, was pretty close. All right, I'll take that as a guess. So 80.18%. So that's how you can use the empirical rule, right? Like I was able to get pretty close without having to actually type anything into a calculator, just by doing a little bit of quick estimation using the empirical rule. So you can see it's kind of handy. But if you want a precise answer, right, you wouldn't put on a test, it's about 80% according to the empirical rule. No, you type it into your calculator. So that's why I'm saying the empirical rule, useful, but not strictly necessary if you want a nice precise answer. So 80.19%. About equal to 0.8019. All right. So there you go. So that's how you can, so again, the question was phrased in terms of what is the probability that the total weight of 8 sumo wrestlers is more than 3,000 pounds. We just rephrase that into what is the probability that the average weight is more than 375. That's it. That's how you use the central limit theorem for sums. I think I asked one more question on here. Let's go see what it was. I really don't remember what it was. Oh, find the 75th percentile of X. Oh, total weight. So X is total weight here. So we want the 75th percentile here. So that just means that we're going to turn the averages into, again, we're going to turn the totals into averages. So we're going to find the 75th percentile of X bar, and then just turn that into a, just turn that into a total by multiplying by 8. So the 75th percentile of this distribution, 75th percentile of this distribution, which is X bar. So we're just going to do inverse normal 0.75 with a mean of 390, standard deviation of 17.68. Inverse norm, so 0.75, mean of 390, standard deviation of 17.68. 401.92. So that is the 75th percentile. Look, let me rephrase that. 75% of all samples of sumo wrestlers at this convention have a weight that is smaller than this, and 25% have an average weight larger than this. So if we want to find the totals, right, since there's 8 sumo wrestlers in our group, we just multiply this by 8, right? If this is the average weight of the 75th percentile, well, then the total weight is that, 3215.4. That's all you got to do. So 75th percentile of total weight of 8 sumo. It's about equal to something I totally forgot while I was figuring out my phrasing. Let's go look at it again. 3215.4. Okay. 3215.4 pounds. There you go. So that's how you convert between averages and totals. You just multiply by the sample size or divide by the sample size, depending on which direction you're going. Okay, I think that's about all I wanted to say here. Let's quickly go back to the notes, make sure I've hit everything. Yeah, that's all I wanted to hit. Yeah, there you go. Summary is really pretty straightforward here. It's not a lot to say, right? So here's what I want you to know from chapter 6 and 7 combined: how to use normal CDF and inverse norm, and when to use normal CDF and inverse norm, which maybe I will draw you a little picture in just a second, actually. And then when to use the central limit theorem, and what the central limit theorem is telling you. Like what it's talking about is, but it's talking about the sampling distribution instead of the population. You got to keep that in mind. And then how to use the central limit theorem, and then how to do it with totals as well. So that's what I'm looking for. Yeah, and I think that's all I want to say. So let me. Oh, actually, pardon me. Let me hit this the when to use inverse norm, when to use normal CDF question. Yeah, let me go ahead and do that right now, because I have a little picture that might help you. So I hope everybody got this far. Data values. If you have data values and you want probabilities or areas, excuse me, my video's done converting. That is normal CDF. So I have data values and I want to turn that into, and I want to find areas. That's normal CDF. if I have probabilities or areas, so percentile, and I want to figure out what the data values are that go with those, it's inverse norm. That's why it's called inverse norm. These two functions are inverses of each other. Right? One of them, like you have data values, use normal CDF to get probabilities. You have probabilities, you go back to data values by using inverse norm. It's a big circle. Yeah, so there you go. That's kind of the last thing I wanted to say there. Let me go ahead and stop sharing this. Yeah, and that's all I have to say about the central limit theorem. So I'll go ahead and end the recording now, and I will see you guys in the next one.